Hi everyone, my name is Thomas Nishcox. I'm a PhD student at McGill University under the supervision of Professor James Forbes, and here to talk to you a bit about our work appearing in the IEEE TRO called Improving Self-Consistency in Underwater Mapping Through Laser-Based Loop Closure. We're sponsored by Voyis Imaging Inc. Voyis makes outstanding underwater lighting and imaging systems, and we've been fortunate to have them as an industry partner. All right, a little background on underwater navigation and mapping. So, subsea operations are often carried out by underwater vehicles. So, AUVs, which are autonomous, and ROVs, which are remotely piloted. And these vehicles often work in very challenging underwater environments. So, many kilometers under the ocean surface, we have dark and relatively featureless environments. And because of that, we often use acoustics to help the vehicle localize. So acoustic measurements, acoustic sensors, great for localization, not the best for mapping, especially if you want to do high precision mapping. So acoustic sensors such as side scan sonars and multi-beam sonars are often used for wide area inspection. Example in figure 2 there of a shipwreck in the Great Lakes scanned with a multi-beam sonar. You can see it's fairly low resolution, not really what you'd like to see on like an archaeological survey. More frequently, industry is moving toward high resolution sensors such as cameras and in our case underwater laser scanners. All right, so for the navigation piece, our vehicles often navigate with the help of one of these over in figure 3. So this is a DVL-INS, which is a Doppler velocity log aided inertial navigation system. So they're very expensive inertial navigation systems, and it's a strap-down solution. So you can go out, buy one of these, and fix it to your vehicle, and it'll help you navigate. Unfortunately, from a research state estimation perspective, these sensors give very limited access to information that you typically need to do state estimation. So all you're getting out of this really is a mean trajectory estimate and often an incomplete marginal covariance. All right, so what we'd like to do is we'd like to combine one of these underwater laser scanners with one of these strap-down systems and use the point clouds from the laser scanner to correct drift over time. So basically moving from one of these prior maps where we see a bit of navigation drift to a really tight posterior map suitable for high resolution, self-consistent underwater mapping. All right, so how we do this is laid out in the paper. Basically, we make submaps from our sensor data. We align them using a fairly standard two-part point cloud alignment pipeline to get loop closure measurements. So in figure 4, that's the delta T rail. And having those loop closure measurements basically allows us to correct our solution, right? So here we have our prior vector graph. This is just with measurements from the DVL-INS. And we sort of massage that, do some work on it, and we basically come up with a couple of between factor terms that allow this yellow loop closure measurement to propagate. All right, figure 6 shows our system overview, basically moving from our raw sensor measurements on the left side. We have our loop closure measurements, for instance, upper right corner. And what comes out of this is our posterior state estimate down in the lower right corner. So on the experimental results side, Voyis has a research vessel, which is this lovely boat over on the left side. We have a sensor rig aboard that research vessel. That's figure 7B, sort of looking down at the top. And among some other sensors on that rig, we have our inertial navigation system in yellow and our laser scanner in blue. And we took these sensors up to Colpoys Bay in Wiarton, Ontario, Canada to run an experiment. So figure 8 summarizes that experiment. Basically, we have our trajectory in green in the northeast corner of figure 8A. And zooming in on that, we can see we have a small shipwreck there. And we can use that shipwreck to produce loop closure measurements and update our trajectory. So figure 9, no surprise here. What we're showing is relative drift on the XY plane. Starting from the blue INS estimate, as you add more loop closure measurements, your estimate drifts less. So again, no surprise there, but we're able to achieve this result without access to raw sensor measurements from our inertial system. Basically moving from our prior point cloud map, where we see high disparity errors, to our posterior point cloud map with low disparity errors. So in summary, we're able to achieve high resolution, self-consistent underwater maps. If you're interested, please come see our presentation at ICRA.